Before writing electron configurations, let's understand the order and organization of electrons in atomic orbitals around the nucleus. Aufbau is German for building up. In chemistry, we use this term to describe how to build up an electron configuration. The Aufbau principle explains that as protons are added one by one to the nucleus to build up the elements in the periodic table, the lowest energy orbitals fill up first with electrons. This means that when writing the electron configuration, always put electrons in the lowest energy orbital first, the 1s orbital. Then place electrons into higher energy orbitals as necessary. This is an energy level diagram we built in an earlier video using the quantum number rules. When writing electron configurations, place the electrons in the lowest energy orbital first, then add electrons into higher energy orbitals as necessary. The order of the orbitals is shown in the first bullet point, but this can be difficult to learn or memorize. There are other strategies. For example, list the s, p, d, and f orbitals according to the quantum number rules shown here. Then, draw diagonal lines starting with the 1s orbital as shown. Then follow these lines in order to know which orbital comes next. You must remember how many orbitals there are, and that up to 2 electrons can occupy each orbital. You'll also notice I've only written the 7s, 7p orbitals, 6s, 6p, and 6d orbitals, and only 4 and 5 have f orbitals. This is because of the periodic table. Let's look at this next. The easiest way to learn electron configurations is to simply follow the periodic table. Usually, you'll be given a copy of the table for each assessment. Simply learn the orbital blocks: the s block, the p block, the d block, and the f block. Notice how the f block appears right after lanthanum and actinum in periods 6 and 7 respectively. Also an important note, helium, on the top right-hand corner, is part of the s block. The d block starts with principal quantum number 3, and the f block starts with principal quantum number 4. We learned in an earlier video that Aufbau is German for building up. In chemistry, we use this term to describe how to build up an electron configuration. The Aufbau principle explains that as protons are added one by one to the nucleus to build up the elements, the lowest energy orbitals fill up first with electrons. Hund's rule. Hund's rule is the lowest energy configuration for an atom is one having the maximized number of unpaired electrons in degenerate orbitals. Let's look at this using the atomic orbital diagram we built in an earlier video. When writing electron diagrams and understanding configurations, start assigning electrons to the 1s orbital first. Notice the electrons are spin up and spin down in accordance with the Pauli exclusion principle. If there are more electrons present, assign them to the 2s orbital. If there are more electrons present, they would be assigned to the 2p orbitals. Notice how these orbitals are equal in energy. They are said to be degenerate or equal in energy. According to Hund's rule, the electrons would be placed in separate orbitals first. Notice how the unpaired electrons are maximized. If more electrons are present, then they would pair to fill the 2p orbitals. If more electrons are present, we'll assign them to the 3s orbital first, and then the 3p orbitals. Interestingly, notice how the next energy orbital is the 4s, not 3d. There's a quirk in the periodic table that we discussed in an earlier video about the Aufbau principle, where the electrons fill the 4s orbital before filling the 3d orbitals. The next electrons, if any, would go in the 4p orbitals. Let's write the electron configuration for neutral hydrogen in the ground state. This means that the electrons equal the number of protons for the atom to be neutral, and the electrons are in the lowest energy state, or orbitals. This is the ground state. Hydrogen is the simplest element. It has one proton and one electron. The electron goes in the 1s orbital. We write 1s1. The second one is superscript. This indicates one electron in the 1s orbital. For the diagram, we'll draw one arrow in the 1s orbital representing the lone electron in the 1s orbital. The arrow can be pointing up or down to indicate spin up or spin down. Recall, if there is a pair of electrons, they must have opposite spins, but this is not an issue for neutral hydrogen. Helium is the next simplest element. It has two protons and two electrons. The electrons go in the 1s orbital, and we write 1s2. The 2 is superscript. This indicates two electrons in the 1s orbital. For the diagram, we'll draw one arrow pointing up in the 1s orbital. This represents the spin up electron, and we'll also draw a second arrow pointing down to represent the spin down electron. This satisfies the Pauli exclusion principle, where two electrons sharing an orbital must have opposite spins. Here are the electron configurations and diagrams for neutral second row elements. Lithium has 3 electrons. We'll write 1s2 to represent the first 2 electrons in the lowest energy orbital, the 1s. The next electron goes in the next higher energy orbital, the 2s. And we'll write 2s1. I have included the shorthand configuration. Notice that the electron configuration for lithium starts with 1s2. This is the same configuration as helium. For the shorthand configuration, we'll write helium in brackets, followed by 2s1. For the diagram, we'll put the first 2 electrons in the 1s orbital with opposite spins, then add the third electron in the 2s orbital. Beryllium has 4 electrons, so we'll add a second electron to the 2s orbital. Moving to the p block of the periodic table, boron has 5 electrons. The 2s orbital is full, so we'll add a 5th electron to one of the 2p orbitals. Recall, there are 3 2p orbitals. Carbon has 6 electrons.
we'll add another electron to the 2p orbitals. Notice, following Hund's rule, we'll maximize the unpaired electrons. The electrons in the 2p orbitals are separated. We'll add another electron for nitrogen. For oxygen's 8 electrons, we'll have to start pairing up electrons in the 2p orbitals to fill them. We'll add another for fluorine. Finally, the last element in the second row is neon. Notice how all the orbitals are full for the noble gas. Let's write the electron configurations and diagrams for the third row elements. These elements include sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. In a previous video on electron configurations for second row elements, we concluded with neon, and we'll continue from here. Sodium has 11 electrons. We'll start filling the 3s orbital by writing 3s1, and we'll add another electron for magnesium, which has 12 electrons. The 3s orbital is now full. We'll now add electrons to the 3p orbitals for aluminum, silicon, and phosphorus. And we'll continue adding for sulfur, chlorine, and argon. The 3p orbitals are now full. For diagrams, we'll start with the diagram for neon, where the 1s, 2s, and 2p orbitals are full, and then add an electron in the 3s orbital for sodium. We'll add another for magnesium, and the 3s orbital is now full. We'll start filling the 3p orbitals for aluminum, add another for silicon, and another for phosphorus. In accordance with Hund's rule, these electrons are separated, unpaired. For sulfur, we'll start pairing electrons in the 3p orbitals. Another for chlorine, and finally for argon. All the orbitals are full of electrons for the noble gas argon. Let's write the electron configurations for the fourth row elements. The fourth row is our introduction to the transition metals and d orbitals. In a previous video on electron configurations for third row elements, we concluded with argon, and we'll continue from here. Potassium and calcium have 19 and 20 electrons respectively. We'll add electrons to the 4s orbital first. You can see these configurations are starting to get long, as we'll be adding electrons to the 4s, 3d, and 4p orbitals eventually. I'll write the shorthand configurations moving forward. You'll notice the elemental symbol for argon in brackets for the shorthand configurations. Next, we enter the D block of the periodic table. These are the transition elements. Recall, there are 5 d orbitals that can hold up to 10 electrons. Not coincidental, there are 10 elements in the d block. Here, we'll add electrons to the 3 d orbitals one at a time. There are 2 exceptions to the rule. Notice for chromium and copper. Only one electron goes in the 4s orbital, while the other electrons start to fill the 3d orbitals before filling the 4s orbital. There are other exceptions like this throughout the periodic table in the d block, but that's outside of the discussion for this channel. We'll conclude the row by going into the p block. Here, we'll add electrons to the 4p orbitals one at a time, concluding with the noble gas krypton.
Valence electrons are electrons in the outermost principal quantum number. These are electrons farthest from the nucleus and can participate in chemical bonding. Core electrons, on the other hand, are electrons in the innermost atomic orbitals or orbital. Note how core electrons can be in more than one type of orbital. The key is that valence electrons are in the outermost orbitals. Let's look at the example of lithium. It has 3 electrons. There are 2 electrons in the 1s orbital and 1 electron in the 2s orbital. The principal quantum number 2 is the highest, therefore there is 1 valence electron. The 2 electrons in the 1s orbital are the 2 core electrons. Let's look at a few other alkali metals, sodium and potassium, and we'll see something interesting. Sodium is a third row element. It has 10 electrons total in the 1s, 2s, and 2p orbitals. Principal quantum number 3 is the highest, and there is 1 electron. Therefore, there is 1 valence electron and 10 core electrons. Potassium is a fourth row element. It has 18 electrons in principal quantum numbers 1, 2, and 3. Principal quantum number 4 is the highest, and there is 1 electron. Potassium has 1 valence electron and 18 core electrons. Do you notice the trend? The alkali metals all have 1 valence electron. Let's look at the periodic table. There's a shortcut on the periodic table. The group number tells the number of valence electrons. Look at the top of the group. The alkali metals are in group 1. They all have 1 valence electron. Hydrogen is not an alkali metal, but it is part of group 1, so it also has 1 valence electron. The earth alkali metals have 2 valence electrons. Let's skip over to the nonmetals. For nonmetals, look at the second number in the group number for the valence electrons. Look at carbon and silicon. Each have 4 valence electrons in their outermost shell. Nitrogen and phosphorus each have 5 valence electrons. Oxygen and sulfur each have 6 valence electrons. You can see from the table The halogen family has 7, and the noble gases have 8. Unfortunately, there are no shortcuts for the transition elements. You can use the shortcut to find valence electrons for alkali metals, earth alkali metals, and nonmetals.